Welcome to part 2 of rational functions. In part 1 we covered some high-level points about rational functions concerning basic graph structure, as you can see right here. We also covered topics such as vertical asymptotes, which is also shown, and we also covered domain. In part 2 we're going to cover topics such as holes in the graph, which you can see right here on the screen, which are also points of discontinuity, and we're going to talk about horizontal asymptotes and slant asymptotes. So the first thing we're going to talk about are points of discontinuity. So if you take a look at this graph that I have over here, you notice right here we have this hole in the graph. We have this point which is a point of discontinuity. And if you look over here, these points are created by canceled factors in the numerator and the denominator of rational functions. So for instance, if I had a rational function, if I just made one up here, if we had f of x equals, and I'll keep it in factored form, if we had x plus 1 times x minus 2 over x plus 3 times x minus 2. Now we know we can, the first step whenever we're working with rational functions is we want to factor the function. And this one's already been factored, so this factor here that we cancel would actually create a space in the graph or a hole in the graph, which is also considered a point of discontinuity. This is a point in the graph where the graph ceases to be continuous. And again, they're created by canceled factors of the numerator and the denominator. So the way this would work is, I've canceled a factor here. I've canceled x minus 2. That's the factor that we've canceled. And then what we're actually going to do, if you look over here, just slightly over here to the left, this hole that we've created is actually a placeholder for a point that really should be there, if you think of it that way. So in every point has to have an x and y coordinate. So this placeholder also needs an x and y coordinate. So the way we would create this hole for the graph that I'm working on, or the function I'm working on over here, the way you create your x and y coordinates is that you take your canceled factor, so we have x minus 2, and then all you would do is just set this equal to 0 and then solve. So you're going to get your x coordinate as 2. Okay, that would be your x coordinate. And then to find your y coordinate, all you would do is substitute this substitute this value into the reduced function, and you'll get your y coordinate. So if we take this, if I take 2, and we're going to plug this into the function now, we're going to do f of 2 equals, and I'm only going to use this part of the function. We're only going to use the reduced part. So if I take the 2 and I substitute it in, we're going to do 2 plus 1 over 2 plus 3. So what we would get here is we would get 3/5. All right? So we would have a hole or a point of discontinuity at the place 2, 3/5. And that's essentially what you do for any holes in the graph, any points of discontinuity. So if we take the example that I have over here, and I'll show you where this comes from, why I have that hole right there. So the first thing we need to do always, we're going to find the coordinates of that hole there with the function f of x equals x squared minus 16 over x minus 4. First thing we're going to do in any of these functions is always factor it. So if I factor this, the numerator is basically a difference of squares, so we're going to factor that into x plus 4 times x minus 4. And then the denominator is just x minus 4. And then the next thing we would do is we would cancel any common factors. Well, I have these two factors here, the x minus 4s, and we can cancel those two, right? Those factors could get canceled right out. So the reduced polynomial now, the reduced rational function, would actually turn into, it would turn into a polynomial now, because now all we have is x plus 4. All right? Which is essentially, if you look at, so this is what we have for the reduced function, and if you graph that, this is basically a line, and if you look at the graph, that's really what we have there. You have a line. So now how do you find the actual hole that we created over here? All we're going to do is take your factor, so we have x minus 4, set that equal to 0, and then we're going to solve for x, so we're going to have our x coordinate of the hole is going to be 4, and then all you're going to do is plug in the 4, substitute the 4 in the reduced polynomial right here. We would have f of 4 equals 4 plus 4, and we would have f of 4 equals 8. So we would have a hole, or a point of discontinuity in the graph, at the point 4, 8, and that's exactly what we have over here, and that's really all it is. All right, and holes and vertical asymptotes and slant horizontal asymptotes are all part of the puzzle that make up these rational functions. As I said in video number 1, these functions can have a lot of different pieces, and holes is just one of the pieces that could be part of this. And I'm going to be right back in the next section with horizontal asymptotes. So now we're going to talk about horizontal asymptotes of rational functions. So if we look at this graph that I have over here, we see this, I'm going to highlight this. So we have this blue line, this blue horizontal line here. I'm going to accentuate that a little bit just so you can see it a little better. So what I have there is, if I look at this, I'm going to draw this out. So this is one of the branches of the graph. I'll actually make this out just a little bit thicker so we can see that a little better. So I have this. Here's my line. This is one of the branches of the graph. And as we continue this out, now if we extended this out, if we went, extended this out to positive infinity, all right, this line would actually get infinitely close to this horizontal line as it went off to positive infinity, but it would never actually reach it. So in the positive direction, this graph would approach this line, and you can see this line here, this horizontal line, is basically just y equals 1. And if we look at on the other side, so I'm going to do the same thing but on the left side, if we take this part of the graph, right, this graph is going to go that way. So as as we're going out to negative infinity, as the graph is going to negative infinity, the line, the end behavior of the graph in this direction is also going to approach y equals 1. So in both directions, as the graph approaches positive and negative infinity, it's going to flatten out and approach this horizontal line. So we could say that graph would have a horizontal asymptote. So it's going to have a horizontal asymptote, just like it has, graphs can have vertical asymptotes, it can have horizontal asymptotes. So as it's going to positive and negative infinity, the graph is going to kind of end, as it's going off into oblivion, into infinity. It's going to approach and look like that horizontal line, y equals 1. And that's really all horizontal asymptote is. What is happening to the end behavior as it's going to positive and negative infinity. So now we're going to come over here, and there's a more algebraic way to calculate that. So I just want to change that out a little bit. So a couple of conditions exist. So what you need to do is you need to figure out the horizontal asymptotes, is you need to look at the degree of the numerator and the denominator of your rational function. So if I look at this function here, we have f of x equals 8 over x squared plus 1. And you're going to look at the degree of the numerator and the degree of the denominator. Well, the degree of the numerator, any constant is always going to be a degree 0. So this is going to be degree 0. And in the denominator, the degree is a 2. So what it says is, the rule here is, if you can see this, the rule says if the degree of the numerator is smaller than the degree of the denominator, you will have a horizontal asymptote at y equals 0, which is basically the x-axis. So if the numerator is less than the denominator, your horizontal asymptote will be the x-axis. So that's the first case. Now what happens if we come over to B? What happens if the degrees are equal? So if we look at this, g of x equals 3x squared plus 1 over 2x squared minus 1, the degree of the numerator, the highest exponent in the numerator is 2, and then it's the same thing in the denominator. They both have a 2. So now what do? We said if the numerator is less than the denominator, like in the first one, the horizontal asymptote is y equals 0, it's the x-axis. What if they're equal? So what is the process there? So all you're going to do, and you see I have it circled here, if the degrees are the same, all you do is you take the lead coefficient, and it's right here. You take the lead coefficient of the numerator and the lead coefficient of the denominator, and that's going to be your horizontal line. So if we took the lead coefficient here, the lead coefficient of my numerator right here would be 3, and the lead coefficient of my denominator would be 2, and all you do is set y equal to that because it's a horizontal line. So that would create a horizontal asymptote at y equals 3 over 2. And that's what you see right over here, 1.5, that graph as it's going to, if I did the same type of demonstration I did before, as this graph is going off to positive infinity, I kind of ran into it, but you get the point. As it's going to positive infinity, this graph is going to approach that horizontal line in both directions. It's going to come this way. It's going to get really close to that, but that's going to be my horizontal asymptote. And that's really what you do. So those are the two conditions. If the numerator is less than the denominator, it's y equals 0. If the numerator is equal to the denominator, you take the lead coefficient of the numerator and the lead coefficient of the denominator, and that's going to give you your horizontal line. Now the last case is going to be, what if the numerator is actually greater than the denominator, and that's what's going to create what's called a slant asymptote, and I'm going to deal with that in the very next section. So I'll be right back with slant asymptotes. So in this section of part 2, we're going to deal with slant asymptotes. And if you look at what I have up top here, slant asymptotes occur when, so this is when you have the degree of the numerator is 1 more than the degree of the denominator. Okay? So if I look at this function here, so when the degree of the numerator is more than the degree of the denominator, you're going to get a slant asymptote. So I have my function here, and I'm looking at the degree of the numerator. The degree of this numerator is going to be degree 2. I'm going to write it like this. And then the degree of the denominator is going to be degree 1 because it's a linear function in the bottom. So when the numerator is bigger than the denominator, for as far as degree goes, you're going to get what's called, you can see it over here on the graph, this slant asymptote. It's not going to be vertical or horizontal, but it's going to look like a line. That's when it's 1 more than the degree of the denominator, when the degree is 1 more. So as this graph, you can kind of see it, as this graph is going to negative infinity, the line of the graph is actually going to resemble this linear function. So it's going to kind of cease it as it's going to negative infinity. It's going to cease to have that curving shape, and it's going to, as it's going to negative infinity, it's going to resemble that dotted line, that slant asymptote. And the way you do it is you're going to use division. So all you're going to do is you're going to divide your numerator by your denominator. And you can use long division, you can use synthetic division to do that. In the examples I have here, I have long division. So sometimes it's a good review to do long division. So, and all you need is your quotient. You really don't, when you're doing, when you're talking about slant asymptotes, all you need is the quotient up top here. You have your remainder down below. You have this 9. You don't really care about that 9 as far as the asymptote goes. All you care about is this top part, and this is actually going to be your linear slant asymptote there. It's going to be y equals x plus 4. All right, and one of the examples, I think example C below, I'm going to do one where we're going to use long division and we're going to find the slant asymptote. So those are the 3 categories of either horizontal asymptotes or slant asymptotes. So the thing to be aware of, and it's right here in the note I have here. So rational functions are going to have a horizontal asymptote or a slant asymptote. It's not going to have both. All right? It could have a horizontal and a vertical asymptote, or it could have a vertical asymptote and a slant asymptote, but it can't have a slant asymptote and a horizontal asymptote. So now what we're going to do is we're just going to classify the examples down at the bottom here, and then we'll end the video. So all I want to do in these 3 examples is determine, you can see it right here, it says determine whether the graphs have a horizontal or slant asymptote and figure out what the actual asymptote is. So in the first one, and remember when you're doing this, you're looking at the degrees of the numerator and the denominator. So if I look at this, the degree of the numerator is 1. Okay, then my degree here is 1. And the degree of my denominator is 2. So I know if the numerator is less than the denominator, and that's fairly easy, that my horizontal asymptote, I'm just going to write it like this, my horizontal asymptote is going to be y equals 0. Some of these are fairly quick. If we go to the next one, if I look at the degree of the numerator is going to be 2. And if I look at the degree of the denominator, it's also 2. So what we said earlier was if the degrees are the same, you look at the lead coefficient. So I'm going to look at the 4 and I'm going to look at the 2. And we create our fraction out of that. So we have y equals, the degree of the numerator was 4, or actually the lead coefficient of the numerator was 4. The lead coefficient of the denominator was 2, and then we can just reduce that. So it's going to be 2. So we would actually have a horizontal asymptote at y equals 2. So that one's fairly quick. Now the next one, we're actually going to use division because if I look at this, the degree of my numerator here is 3, and if I look at the degree of the denominator, is the 3, and the degree of the denominator is 2, so I know this one is going to have a slant. All right, so this one is going to have a slant asymptote. So what we're going to do here is we're going to do some division. So I'm just going to use my sketch pad over here, my scratch pad. So this part down here will be my divisor. So we're going to do 2x squared plus 2x minus 1. And the top part here, the 4x cubed, will be my dividend. All right, so this is actually a good little review of long division. So what do you do for long division of polynomials? We're going to look at, you need to look at the first term of your divisor, and you look at the first term, we only have one term of your dividend, and you're going to, what you need to do is you need to multiply 2x squared by something over here to equal 4x cubed. All right, so the only thing that's going to work here is going to be 2x. Because 2x times 2x squared would give me 4x cubed. So if you multiply 2x times 2x squared, we're going to get 4x cubed. And then I also have to multiply the 2x times both of these. Right? So 2x times this 2x is going to be 4x squared. And then 2x times negative 1 is minus 2x. And now the thing is, when we do division, we have to change the signs here because we're subtracting all of these. So these signs will actually change. I'm actually going to change the color here. So this was positive. This first term was positive. We're going to change that sign to a negative. This one was positive. Oops. So we're going to change this one, and this was a 4. We're going to change that to negative. And then this one was positive or negative. We're going to change that to positive. We just changed the signs. So when we add down the columns, these are going to cancel, and we're going to bring these down. We're going to bring down the negative 4x squared, and we're going to bring down the 2x. So how do you know when you can stop dividing? Well, you have to look at the degree of your divisor and the degree of your remainder. You stop when the degree of the divisor is more than the degree of your remainder. So right now the degrees are equal. They're both 2. I have to do this one more time. So what I need to do is I need to make 2x squared look like negative 4x squared. So I'm going to multiply by a negative 2. All right, that's how we equal that. So we're going to do negative 2, and we're going to multiply negative 2 times 2x squared. So that's going to be negative 4x squared. And we're going to do negative 2 times the 2x, that's going to be minus 4x. And we're going to do negative 2 times negative 1, that's plus 2. And then again, we're going to change all the signs. So this one is going to change to plus. This one is going to change to plus. And this one will change to a minus. All right. And then we're just going to add down the columns. So the lead term here is going to cancel. The middle term is going to become 6x, and then we'll have minus 2. And then what I said to you was, I don't really care about this remainder as far as the slant asymptote goes. So all you care about is your quotient. So my slant asymptote would be y equals 2x minus 2. And that's what we would have over here, y equals 2x minus 2. The remainder here is really not important for the asymptote. So when we graph this, when we put all the pieces together, and that's what we're going to do in the next set of videos, you would have a slant asymptote that would actually look like this. You would have this slant asymptote, if I did it in red, and this would be the line y equals 2x minus 2 if we did it out. Okay, that's not what I have there is not 2x minus 2, but you get the point. So hopefully that made sense to you about the slant asymptote and horizontal asymptote. And in the next set of videos, what I'm going to do is we're actually going to put all the pieces together. As you can see below, it's kind of like a little trailer for what's to come. This is our strategy. This is going to be in video number 3. These are all the steps that are going to be involved in graphing rational functions. So I will continue this series on rational functions with the 3rd video when we put all the pieces together and we'll do a complete graph. Okay? So take care.